Okay, so 5.4 is triple integrals. You can see your learning objectives there. We have some, we have a theorem, and you can see below they have it broken down into a lot of stuff. And we have the definition for the limit with 3 integrals. So I am going to give you guys some time to write that down. You can see it's not a super long lesson. Yeah. All right. It's about to use the mouse to move the tablet. Okay. So what you're going to find is that the majority of this is just going to be staying organized and keeping everything nice and tight until you get to the end. So trying basically not to get lost in the sauce. It's going to be long, maybe not necessarily hard, but it's going to be long problems because you have to do 3 intervals within one. So the order of the integration is specified in the problem. So it tells you what to do, literally. So we want to integrate with respect to x first, then y, and then finally z. So, please don't feel like these are interchangeable. If they're given to you in that order, that is the order you have to do it in. Now, if you want to play around, more than likely you'll find out that they'll end up being the same answer, but don't just go, well, I'm just gonna do whatever I want. Do the problem the way they give it to you. So, all right. So I'm not gonna do the rewrite of the problem. You guys can see it there. I'm gonna go to the first step. So we're gonna have the 0 to the 1 for the z again, 2 to the 4 for the y, and then we're gonna go ahead and do our integration. X squared over 2 plus x y z squared. And it's going to be from -1 to 5, and then dy dz. And then you plug in and evaluate. Then you're going to end up with 0, 1, 2 to 4, and you're going to end up with a 12 plus 6 y z squared dy dz. And then now we want to evaluate with respect to y. So we'll have 0 to 1 for the z, 12y plus 6 y squared over 2 z squared. And then from 2 to 4 dz. Again, evaluate 0 to 1. Gonna end up with 24 plus 36 z squared dz. And then 24z plus 36z cubed, sorry. Over 3 from 0 to 1. And then lastly, if you evaluate, you end up with an answer of 36. So again, if you would have sat there and done it the opposite, As long as you move your evaluation portions and keep everything the same, you should end up with 36 all three times, but or however rearrangement you want to do, but I would just leave it the same. All right. This next one says evaluate the triple integral, and then it gives you the region, and then it shows you the figure. So what you'll notice is that the order is not specified, but we can integrate the integral in any order without changing the level of difficulty. So you could choose to integrate y first, then x, then z, or you could do x, then y, then z. And again, what you're going to find out is that you're going to end up having the same answer. Okay, so we'll try really hard to get both onto this slide. If it doesn't work, it doesn't work, and we might have to go to the next one. So we'll do our best. So 1, 5, and then -2, 1, and then 0 to 3, and x squared, y, z, and then dy, dx, dz. All right, so then we're going to go 1 to 5, -2 to 1. Then it's going to be x squared, y squared over 2, z, dx, dz. I forgot to throw in the evaluations. It's going to be 0 to 3, dx, dz. 1 to 5. And then -2 to 1. And then if you put in your evaluation, you get 9/2 x squared z dx dz. And then 1 to 5. And then it'll be 27 over 2. Oh, sorry. Skipped. Went to the evaluation step. So 9/2. And then x cubed over 3z, -2 to 1, dz. 1 to 5, 27 over 2, z dz. And then that's going to be 27 over 2. Sorry. Z squared over 2, 1 to 5. So your final answer here is going to be 162. And then what we can do now is, so this one was doing what? Y, then X, then Z. We can do another approach, and then we can do X, then Z, then Y. And what we're going to see is that it's going to end up being the same thing. So I will rewrite it here just in case you guys need it. So now it'll be 0 to 3, 1 to 5. And then -2 to 1, x squared, yz, dx, dz, dy. And then I'll try to squeeze it in right here. And then that's from -2 to 1. And then you get 3 YZ dz dy. And 0 to 3, 3 y squared over 2. Oh, and this is why you guys have to be extra careful on your order. One, 0, 3, 36, y, y, y squared 36, y squared 2, 3, 18, 0, yep, 160. So that's just basically proving to you that you can, in fact, get it as long as you keep consistent with what is where. All right, so we do actually have a page of some notes here. Yes, because I had to add in a slide. So go ahead and take your notes off of it. All right, so here's your theorem. Here's nice little image for it. Okay, so the next problem we're going to do is evaluating a triple integral over a general bounded region. So the triple integral of the following function over the solid tetrahedron bounded by the following. So this image is going to help you figure out your region. So what you know is E is XYZ now, and X is from 0 to 1, Y is from 0 to 1, 1 minus X, sorry. And then Z is from 0 to 1 minus X minus Y. All right, so then the triple integral, I'm not going to write I'll write it up here. Okay, so if you want to be most correct in your solutions, you should have something that looks slightly like that in in everything you start off to do. For the sake of like us getting all of our answers on one slide, I'm not doing that. You certainly should and may and probably should do it, but I am not. And I do apologize for that, but I'm trying not to make our notes absurdly long. All right, 5x minus 3y, and then it's going to be dz dz dy and dx. To simplify the calculation, the first integral, the first part here, this section, we're going to focus on just doing that integration. So they're kind of breaking it even further down, but so let's look at it. We have 0 and then 1 minus x minus y, and then the 5x minus 3y dz. So basically you're going to have 5x minus 3y times 1 minus x minus y. So then now you're moving on to the y portion. And it's going to be the 5x minus 3y, 1 minus x minus y dy. And then that's going to give you 5x minus 3y, 1 minus x minus y dy equal to 1/2 x minus 1 squared 6 x minus 1. So finally, we're going to evaluate from 0 to 1 for the x, 1/2 x minus 1 squared, 6x minus 1 dx, and you're going to end up with 1/12. So if you really wanted to, you would rewrite back at the top part and say it was equal to 1/12. But I mean, there you go. Now they're obviously not giving you all the connector pieces, so that's why everything builds. Okay. This one's saying find a volume by evaluating a triple integral. Find the volume of a right pyramid that has a square base and vertex point, and it looks like the following figure. So in this pyramid, the value of z changes from 0 to 1, and at each height z, the cross section of the pyramid for any value of z is the square -1 plus z 1 minus c times -1 plus c 1 minus c. So that is how you find your e, by figuring out this section and how you would write it. I'm so sorry, guys. Okay. So 0 to 1, then negative 1 plus z, 1 minus z, then 1 plus z, 1 minus z. That one doesn't match. Nope, it definitely has it written negative 1 plus z down here. Alright, try it either way. I'm gonna write down for you the solution if you want to play around with it later and see if putting this piece in for this gets you the same answer, or if they have an error. They could have an error. I'm just gonna write it down for you guys because I just want us to get through this one. Someone definitely let me know if you end up changing that out. If you end up with a different answer, we'll go over it again with that answer. 0 to 1, negative 1 plus z, 1 minus z, and then 2 minus 2z dy dz, and then 0 to 1, 2 minus 2z squared dz. So then if you finish it out, you're going to end up with the volume of the pyramid. I guess I should spell it out because that's really delta here. Mid is 4 units cubed. Okay. Still hopeful we're gonna get out kind of early. Okay. So it says changing the order of integration. Consider the integrated integral. The order of integration here is first with respect to z, then y, then x. Express this integral by changing the order of integration to first be with respect to x, then z, then y. Verify that the value of the integral is the same if we let the following function. Okay. So here's some really nice images. So before we even go through setting this up, if you look at the images, if you consider what we've already done, then hopefully everyone that's been paying attention, including myself, should have the following hypothesis. What should that hypothesis be? What do you think should be the outcome if we're going to change up the integrations? I know somebody knows it. Correct. Yep. Excellent. Yeah. So again, as long as you are making sure that your evaluation points are matching with your order, and then you should end up with the same answer no matter what. Very good. So here is what we know for our E. We have X, Y, Z. We have 0 to 1 for our X. We have 0 to X squared for our Y. And we have 0 to Y squared for our Z. Okay. And then that's going to give us basically this. And that's going to be equal to our E F X Y Z dV. Okay. So we need to express this triple integral. And then knowing the region from the figure, we can kind of change up what's going to happen, right? So on the XY plane, D1 would be, and we may need to get more slides for this one. And then that one you can actually keep going. Oh, okay. It's going to be, so for D1, it depends on which way you want to integrate, but those two are the same. Both of those can be seen as D1. D2, I have X, Y. It's going to be, sorry, it's going to be YZ. The last one is XZ. Okay. All right, so that's as far as like what you would need to do just to set up most of this problem. So we can now also describe the E a little bit differently as well, based on everything we just found. So let me give you what that new E would look like, or I guess a different version of E. And then what we would do then is we could look at the problem a little bit generically and then plug in. So that's probably going to be the last part I do on this slide, and then I'll do the rest on a new slide. Hopefully that will be just 2 slides is my hope. So we would have y is going from C to D. Z is going to go from V sub 1 to V sub 2. And X is going to go from Y in here like this. U sub 1 YZ to U sub 2 YZ. And then F X Y Z dx dy or dz dy. And then that goes to 0 to 1 in the y, 0 to x squared in the z, and the square root of y to 1 in the x. Again, f x y z d x dz dy. All right, and then now is when we take this part into effect in the next slide. So we only have a couple more examples left. I definitely think we're going to get done hopefully before the 7:30. So just bear with me. I'm doing the best I can. All right. So 0 to 1, 0 to x squared, and then 0 to y squared, x, y, z, dz, dy, dx. Okay, that's the first set that we're doing. Who knows? We might end up with even more space. I don't know. So 0 to 1, 0 to x squared, and then you're going to have x, y, z squared over 2 from 0 to y squared, dy, dx. And then 0 to 1, 0 to x squared, x, y to the 5th over 2, dy, dx. 0 to 1, x, y to the 6th over 12 from 0 to x squared, dx. 0 to 1, x to the 13th over 12 dx. And that final answer is 1 over 168. So at this point, if you really wanted to like cheese something along, if you thought your answer was right there and you were like, there's no way I messed it up, then you literally probably could in a homework be like, it's this. And as long as the problem didn't say to show your work for everything, you could probably quit there. But what we'll do is we'll just keep working it from the different options here. Just to prove that we are gonna get it, get it there. So you can see that it's really important though to have your initial setup so you know what each piece is. Okay, so All right. Thankfully, this is the last time we have to do this. I guess they just assume that you can see it's going to keep being the same answer. And that again is going to be 1 over 160. So the answers match. All right. All right. Okay. So changing integration order and coordinate systems, evaluating the triple integration where E is the region bounded by the paraboloid that's given and the plane 4. You see it in the picture. All right, so here's what we know based on this nice little picture. What we know is that I will probably have to put in another slide. But aside from that, we know that E is equal to -2 to 2. Then it's x squared y 4. And then negative y minus x squared. Okay. So then that makes our triple integration, this part, become -2 to 2 x squared 4 negative square root of y minus x squared to the square root of y minus x squared square root x squared plus z squared dz dy dx. So this expression is difficult to compute. Consider the projection of E onto the xy plane. So what we would be looking at there is a circular disk. That would be x squared plus y squared less than or equal to 4. If we keep that in mind, then what we would have would be -2 to 2 x squared to 4 negative square root of 1 minus x squared square root of y minus x squared plus z squared dz dy dx could be rewritten as negative 2 to 2 negative square root of 4 minus x squared 4 minus x squared x squared plus z squared to 4 x squared plus z squared. And then it's going to be dy dz dx. Right? Here, the order of the integration changes from first being with respect to z, then y, then x, to being with respect y, then z, then x. It will soon be clear how this change can be a benefit to the computation. So what we're going to do next, I'm so glad I have for this because yeah, we're gonna need them. So we're gonna get started with this. And dz dx. All right, so now we're going to use the polar substitutions, and those are x equal to r cosine theta, z equal to r sine theta, and then dz dx is going to be r dr d theta. So this is essentially the same thing as when we use polar coordinates in the xy plane, except we are replacing y with z. So consequently, the limits of the integration change, and we have r squared equal to, so we can do this because we would have r squared equal to x squared plus z squared. All right, so in case anyone is screaming that we can't do this, we can. All right. I had another slide. So, negative 2 to 2. Negative 4 minus x squared. 4 minus x squared. 4 minus x squared minus z squared square root x squared plus z squared dz dx. Just giving it to you guys the way they have it, so you got to bear with me on all the steps. So 0 to 2 pi, and then 0 to 2, 4 minus r squared, r dr d theta, 0 to 2 pi, 4/3 r cubed minus r to the 5th over 5, 0 to 2 d theta, 0 to 2 pi, 64 over 15 d theta would give you 128 over 15 pi's on top. literally 3 slides, 1 problem. But in my defense, I wrote pretty big. But look, we're gonna get done pretty soon. All right, last problem. Last problem comes with a theorem. And then we're gonna try to find this average. Okay. So says average value of a function of 3 variables. If the function is integratable over a solid region E with a positive VE, then the average value of the function is the following. Note that the volume of VE equal to triple integrals 1 dV. So finding the average temperature, the temperature at the point XYZ of a solid E bounded by the coordinate planes and the plane x plus y plus z equals 1 is T of XYZ equal to x plus y plus 8z plus 20 degrees Celsius. Find the average temperature over the solid. So we want to use the theorem given and the triple integral to find the numerator and denominator, then do the division. Notice that the plane x plus y plus z equals 1 would have, so this plane would have intercepts at 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that the region E would look like X, Y, Z, 0, 1, 0, Y, X. What's wrong? But friend. Sorry. Z 1 minus X. Okay. All right. Okay. So then we're going to start with this idea. And we're going to rewrite it. We're almost done, guys, I promise. So 0 to 1, 0 to 1, and then 0 to 1 minus X minus Y. It's going to be XY plus 8Z plus 20 DZ dy dx. So that is going to end up being, if you work it all out, 147 over 40. Then what you're going to do is you're going to evaluate this part. So V of E 1 dV is going to be 0 to 1, 0 to 1 minus X. Oh, this was a 1 minus X up here too. And then 0 to 1 minus X minus Y. 1 dz dy dx. And that's going to be 1 over 6. So to find the average, you're gonna have 147 over 40 over 1/6, which is the same as doing 6 times 147 over 40, which is 441 over 20 degrees Celsius. All right, that is everything for lesson 5.4.